Good afternoon, colleagues. I note that a few of you, your microphones are muted. I'm just going to use the next 4 minutes to unmute all of you and to give you access to your microphones as well as your cameras. Thank you so much for making time to join us this afternoon. Okay, I think everyone now has access to their microphones as well as their cameras. If I could just have a thumbs up to confirm. I see Dr. Mumbe has also joined. Welcome, Dr. Mumbe. Right. Just a thumbs up. And congratulations, Dr. Mumbe, on your second publication that I saw this year. You've been a productive researcher, I must say. 2 publications in a time span of less than 2 weeks. Pretty impressive. Okay, colleagues, just 2 more minutes before we get started. Philip, how are you today?
Hi, Renny. Can you hear me?
I can hear you perfectly. Just to
Perfect.
test our system, just try and project your slides before our clock strikes 3:30.
Yeah.
Just double check if you can present your slides.
I can't share the slide. It's disabled.
Okay, so let me see what we can do about that. Just want to see if I can add you as one of the core conveners. Can you try again?
Yeah.
Perfect. Okay, I can see your slides, and I would want to assume everyone else can as well.
Perfect.
I see Professor Stefan Nora has joined. Welcome, Prof. Nora.
Okay, thanks a lot, Renny, that you gave me the rights to release my micro and my camera. Hello, Renny, thanks for organization, and hello, Philip, thanks for your input today. I think we still wait for a few minutes, or Renny, and then you may make a first introduction. Yeah, I can say some words, and then Philip would go ahead. What do you think? That's okay.
I think we should start right away because the clock is saying 3:30. Just
Okay.
to be mindful, a few of our colleagues from Namibia have been on the line since 2:30, so they've been on this platform for more than an hour.
No, sorry for that.
So for that reason, I think it's best we start, and this way we are able to end on time as well. So good afternoon, colleagues. My name is Reni Munyai. I will be your moderator for today's webinar, which is titled Flood Forecasting and Heavy Rain Protection Through Hydraulic Modeling. Our presenter today is Philipp Rinkel, who is an experienced water engineer and hydraulic modeling professional at Aquantec in Karlsruhe, Germany, and his expertise includes the development and application of surface water models and groundwater models. Philip, welcome and thank you for making time to share with us insights on this topic. But before we get started, I'm going to hand over the platform to Professor Stefan Nora, who is the PI, so to say, for the WaMiSAR project under which this particular webinar is being delivered. And the WaMiSAR project, Prof will give you an overview, and we'll also give you an overview of our funding through the Water Security in Africa funding instrument and our financiers, so to say. This webinar is co-convened in collaboration with Potsdam University, Karlsruhe Institute for Technology, and this particular session with Aquantec, as well as the Namibia University of Science and Technology. Prof, over to you. Thank you.
Yeah, thank you very much, Rennie, and especially also for all of your efforts to organize this and also for the openness of the NAST to cooperate with us. Yeah, we are the team WaMiSAR, and we are funded by the German Ministry of Research, Technology and Space, and WaMiSAR, that is a project on sustainable and climate-adapted water management of mine water in the Southern African region. So that also includes South Africa, Botswana, and Zambia. And we have this nice education network financed in our project so that we can also support such webinars. Also exchanges with Germany for students and PhD students as well as postdocs, if there's an interest in that. And I think we still are also looking on the side of NAST for additional master students or bachelor students to work within our projects. That means either on revegetation issues, water balance issues of mine water residue deposits, or on groundwater remediation issues or soil and sediment remediation issues related to pollutions from mining activities. So we are focusing in the moment, especially in Namibia, on the Tsumeb deposits, on the deposits of Otjihase and Matchless near Windhoek, as well as on the deposits of Rosh-Pina, and we are very thankful to the associated mining companies that they also support our intentions and our work. So that is a little pre-introduction from my side. We will be funded by the German ministry until the first half of 29 and first half of 28. So time is running, and if you're interested, you are always welcome to contact me personally or Rennie, or even after this little presentation here, Philipp Rinkel von Aquantec or any other person. Just come and visit our homepage. That's just easy, wamisar.info. There you will get more information about that. I also want to say thanks to Teba, who is the coordinator from Germany, from KIT. And she's a little bit like a counterpart of Rennie and also helps to organize all the things around the education network as well as around our research network. So thanks a lot for that. And now I hand over to Philipp, and I'm very curious on your presentation. Thank you, Philipp.
Thank you for this introduction, and thank you, Teba and Rennie, for giving us this platform. And welcome everybody to today's webinar about the topic flood forecast and heavy rain protection through hydraulic modeling. My name is Philipp. I'm working at Aquantec as an hydraulic engineer. We are located in Karlsruhe, and I'm telling you a few seconds about us so that you know a bit more about our and my background and where I'm coming from. So Aquantec is an engineering company focused on modeling in 3 different topics. Let's say the first is hydrology. We are doing precipitation runoff models and water balance models, and we use them for dimensioning of reservoirs or dams or other retention structures. The second one is the hydraulic part, where I mostly work on. It deals with 1D or 2D modeling and even coupled 1D, 2D modeling of surface water. And we use them for flood forecast modeling, for example, as well as heavy rain risk management. And the third part is the groundwater modeling. But today is it's more about how flood forecasting and flood protection is organized here in Germany, and what role are the models playing, especially. So to give a short overview, we live in times of climate change, and this causes increasing weather extremes. We have frequency and the intensity of the rainfalls are increasing, and this all leads to floods. And our aim is always to protect life and the health of people, and also to give some points to do a good disaster management if something happens. So we want to prevent some impacts. On the one side, there are economic impacts, like when you have a damage on your infrastructure, which are, for example, streets or schools or even worse, hospitals. You want to prevent costs for repairs and reconstruction. And of course, you have economic impacts on agriculture and industry when all these, when a flood comes and destroys all your agricultural fields. And on the other hand, there are the environmental impacts, such as like soil erosion, or when chemicals and oils or other pollutants are set free and just flowing around. So you see, the flood and the flood protection is really a topic of social and political relevance. The flood can occur from different reasons. So there are floods due to just river floods with a rising water level in the river, and then at some point it's just flowing out and flooding the area. Then we have floods due to heavy rain events, or even floods due to groundwater. In this presentation, I will focus about the river floods and the heavy rain events mostly. So if a flood happens, we can see pictures like this. You can see on the left side there's a street on the highway that's flooded, and you can't drive there anymore. And of course, the water will accumulate in deeper locations, just like on the right picture under a bridge, and you have a massive disaster. Let's say it like that. And after that, we always say what could have been done and why did nobody expected this event. And what we really think about is how can citizens be warned in advance so they can evacuate themselves, and how do I know if and when I'm at risk. So therefore, we have over 300 steam gauges in Baden-Württemberg. This is a state in the southwest of Germany. And only there are, well, these steam gauges are in all of them states, but in Baden-Württemberg are over 300. And these are continuously monitoring the level of the water level and the discharge in the stream. So actually, they are measuring the water level, and then they have a curve and see the discharge for this exact cross section at this gauge station. So we continuously know how high is the water in these over 300 rivers. And you, as a citizen, you can just go to this website. Here you can see the state of Baden-Württemberg, and all these points and colorful dots are these gauges. These are colored in different colors depending on how much water is flowing there. So the blue colors are just the middle discharge, so nothing special. The blue is a bit higher, but it's still below a 2-year flood, so it's no panic at all. So you can just see this map, see where you live, and then you can click, for example, on one gauge and see what's happening here. If we do that, we have this graph, And there we can see exactly how was the water level rising and going up and down in the last, it's 4 or 5 days, what was happening in the past and how high is the water level now. But and for all these individual gauges, we have a statistic. And so we know how high will the water be if a 100-year flood will occur, or if a 50-year flood or 10-year flood will occur. And we know the water level, which is, for example, this is the statistics for the River Rhine. It's a pretty big river and part of the border to France in Germany. And we can see a 100-year flood is about 9.3 meters high. And if this occurs, we have a discharge of 5,300 cubic meters per second. So, but this is just a statistic. And of course, the statistic is fed with data from the past. So we know what happened in the past, but we are interested in what's happening in the future and what does this mean for me and my future especially. And therefore, we have this model-based forecast for a lot of these stream gauges. So as you know, there are different weather models running continuously. So we have really a lot of different scenarios, how the weather will change, how much precipitation is estimated in the next few days. And all these weather forecasts and different scenarios are put as input data in the hydrological forecast model. And so we have a flood forecast as a result. Well, all of these different forecast scenarios are run in a specific hydrological model. So we have one scenario dealing with the worst case scenario, like it's raining really very, very much. And then we have one scenario from the weather forecast where it's raining the least, or yeah, not that much. And so we have a range where we have a range of these forecasts. And you can see the blue line is what happened in the past. This is where we are now. I took this picture on the 24th November. So we are here. And then we have for the next few hours or even a day, it's all the weather forecast scenarios are pretty much close to each other. So also the flood forecast doesn't have that much of delta. And then they drift to the up and to the down. And we have one scenario for the worst case, one scenario for the best case. And this pointed line is for the highest probability. So what's going to happen with the highest probability? And if we now want to check if all these forecast models are as good as they pretend, I did the check back then in November. So we are now at the 24th of November, and I looked up 2 days. So on the 26th of November, midday, let's say we have a water level that is estimated around 5 meters. And then 2 days later, I checked again. And indeed, we were at 5 meters on the 26th. So the weather forecast was pretty good. But as you maybe have seen, the characteristics of the wave has changed. So we now have this lower peak at the 27th and the higher peak at it's the 29th. And when we look back, I'm going one slide back. We have this double peak characteristics, and they're both equally high. And then they change to one smaller peak and one bigger peak. And this is due to the updated meteorological forecast data, because they have updated in the meantime, and the forecast model, the hydrological model, is fed with these data. Of course, the forecast data has updated. So let's imagine we live somewhere near of this gauge, and we ask ourselves, what does this forecast mean for me personally? Because all of this is happening in the river. That's interesting, yeah. But actually, the people, they don't live inside the river. They live left or right next to it or somewhere near. And they ask themselves, when will my house and when will I or my family or my life will be at risk? So therefore, we have these flood hazard maps. It's short in Germany HWGQ, but it's in fact a flood hazard map. And you can also have access, so everybody has access to these maps with an online viewer that's free. And this online viewer provides information on the endangered areas and for the water depths in the event of flooding for different scenarios, like for a 10-year flood, 50, 100-year flood, or an extremely flood, which is often just a factor added to the 100-year flood. So you can see how likely is it for me and my house to get flooded, and where's the water coming from, and where are safe areas if I need to evacuate myself. So I now just took a screenshot from a small city somewhere north of Karlsruhe with a complex situation of rivers. You can see one river is going here from south to north. Then there's coming one to it well, in the south of this city. One is running in the north of it, and they're all flowing together here. So it's a kind of complex hydraulic situation when it comes to the rivers. And you can see in the map, we have different blue colors. And the really dark blue, like here, are the areas that are flooded in a 10-year flood. The bit more lightly blue is in a 50-year flood. Then we have the 100-year flood area and the extreme flood area, which is, for example, here. So, for example, if you live somewhere in these houses, you can check, my house is getting flooded in a 100-year flood, but not in a 50-year flood. And you know, due to the statistics, how high is the water level at the gauge for a 50-year flood. And so you can just have a look. If it's near this water level, it's better to evacuate, or if it's below it, you're staying safe. And also we have these points in red or in green. And these are bridges. So every point is a bridge, and the color indicates if this bridge status is, if the water level already touches the bottom part of the bridge, or if it's far below the bridge and it's safe to just run over it with a car. Like, for example, here on this highway, this bridge is very high, and you can just run over it, even if it's a 100-year flood. But if you want to use this bridge, this is probably a much more lower bridge. The water is already touching the bridge and it's unsafe to go over it. And these information are important for you if you want to evacuate yourself, but also important for the police or firefighters or other helping people. And now we are asking ourselves, how do we get to these maps? And this is really when we now will focus more on the hydraulic modeling part in this webinar, because to produce these flood hazard maps, we use hydraulic models, hydronomeric hydraulic models in different types, and it depends on your aim, what you really want to do and how is the situation, if you use a one-dimensional or a two-dimensional hydraulic model. So the one-dimensional is good for flow simulations on a straight river with or without any heavy left or right turns. And the real good thing about one-dimensional modeling is the fast simulation times. So this is what is often used when it comes to flood forecast, because you really need to calculate very fast to do the forecast. Yeah. And on the other hand, you have the two-dimensional modeling. This is good for floodplain mapping and urban flood simulations when it's really heterogenic. And well, you can calculate a detailed surface runoff in irregular terrain, like when there are buildings or streets in the way of the flow path. But of course, you need highly detailed topographic data, and you need data for the buildings, where are streets and walls and whatever. And when you have decided which kind of model best fits to your question, you need or we need some input data. Of course, the first thing we need to do is to give our model some water. So we have either have a wave like here. These are hydrological hydrographs for gauges, like 100-year flood was measured, and you really know the wave and how the 100-year flood was going through that gauge. So you can use this, or you have just one value, like the 5,300 at the line which we just saw. Then you can use a stationary input data. And then to build up our river as exactly and accurate as possible, we use measured stream profiles. So what you can see here now is a really special profile because it's even a bridge. So can you see my mouse? I don't know. I can use the laser pointer. Yeah.
We can see it. Thank you.
Yeah, perfect. Yeah, you can see this is just normal in green is the riverbed. Then we had a water level at the moment where these stream profiles were measured. It's in blue, and then in red we have the structures of the bridge. And of course we need to know how low this point is, for example, because when the water level touches this point, the bridge is not safe anymore to run over it, and it would get a red point in our flood hazard maps. Then we need Then we need some more input data for the area, the larger areas. There are 3 different types of input data we hopefully have. The first thing is the green laser data. These are high resolution LiDAR-based surface data. And a few years ago, it was really new because these LiDAR data were able to even produce data under the water surface. So the standard LiDAR-based methods just return the water surface and you couldn't look through. But with this so-called green laser, it was able to really look through the water surface and detect the riverbed like it is. And this provides detailed elevation data for modeling for our riverbed. And it's essential, for example, for representing really small-scale structures, such as sandbanks or other irregularities under the water surface. Then we have the terrain data. This is, well, I think most of you already know what a digital elevation model is. So we can see on this picture, the red areas are high, the blue areas are low, and the green areas are somewhere between it. And you can see what I just mentioned. In the river, everything is blue. So the LiDAR used here just reflected on the water surface and couldn't get through. So, but on all other areas, these are good data, and it represents the ground level without vegetation and gives us for our model building the fundamental topographic basis for the 2D model. Then we have these land use data. These land use data defines the surface characteristic that influence the flow behavior when the water is flowing over the different surface types. For example, we often pretend that water can't really flow through buildings. So we disable buildings or even clip them out of our models. And the roughness values are orientated on the land use data. So the roughness values are the what's here called KST. And these are responsible for the flow resistance and for the velocity that the water is flowing over different surface types. So as you can imagine, the water is, for example, on grassland, it's flowing much slower than it would flow on a street, because the surface is just much more rougher on a greenland or grassland, and this comes with the KST. So if you have any data that can be used for the calibration of your model, these KST or roughness values are the part where you can adjust your running model to the data that that will be used for calibration. And what we then finally have is our two-dimensional mesh model. And you can see here on the right side the different land use types, well, in different colors. Blue are the buildings. Yeah, well, all the other colors are different. Land uses like grassland or greenland or streets here in this violet color. The bridge is, of course, not running through because we want to calculate the water flow. So we have here the riverbed in this yellow color. And the mesh is, as we say, as dense as necessary and as wide as possible, because the more dense your mesh is, the more nodes you have to add on it. And for every node that's in your model, you have to, or not you, but the software has to do the calculation. And the more calculation has to be done, the longer the simulation times are. And we want to save time, so we really try to adapt the density of the mesh to the topography. So when we look at, for example, this example I brought, you can see on the left and on the right side, it's the same part of a river. On the left side, the colors represent the elevation. So red is high and blue is low. And on the right side, you can see that the colors represent different land use data. For example, buildings in blue, or the riverbed, the standard riverbed in this yellow. Then there's a low water riverbed in blue again, a vase in this violet or pink. And all these material data have different roughness values. So you can, yeah, it's a really heterogenic area here. And we now have our final two-dimensional mesh or hydraulic model. And we can use this model to answer different questions. Like the first thing is we can really calculate, and yeah, we can calculate the flood hazard maps to see how water is flowing and where are endangered areas. And also we can calculate the effects of ecological structures on flow characteristics. To give you a little bit of background, we have a European law that dictates us to have a good condition of all water bodies. Also the flowing water bodies, so rivers as well. But many rivers in Europe, they have been straightened or corrected, and these had large negative impacts on the environment. And so it's often asked to renaturate or to insert ecological structures into the river, like it was done here with all these little piles and structures, to really bring back a greater biodiversity again and to fulfill this European law. And the third point we can do with these models is to calculate the effects of new buildings in potential flooded areas and how to build them adapted to the dangers of flooding. That's what I'm coming to next. For example, we had a project in this area, and well, here was a school, but the school was too small. They wanted to build a new building because they needed more rooms, and they wanted to build it directly here, as you can see. And this school was unfortunately between two rivers, and when a flood is happening, they got flooded really bad. So we were asked to do some model runs and to calculate how water is flowing and what they can do to still build their school or their new rooms, because they really needed it. So all of these orange points you can see, these are terrestrial profiles measured. So profile here was even a wall for flood protection. We had some bridges here. And with all these data and the digital elevation model, we built our two-dimensional model. You can see again, here was the school. There is the flood protection wall. And this shows us the elevation, for example, red is high, blue is low. Here was a soccer stadium, and we have this river coming here. This river is coming here, and then they're flowing together. And we needed some input data. That's why we looked at the statistics, how much water is coming in a 100-year flood. And this was for the upper river. It's the so-called River Dill. It's about 370, and at the Lahn it's 650. And we included the hydraulically relevant structures like bridges, or even more complex bridges like you can see here with these arrows. We had some sloping ramps coming here, some weirs, or on the bottom right picture, we even had a fish ladder. And we needed to include all these relevant structures to our model to calculate how is the situation here and how can we prevent a new building from getting flooded. And also, after we finally built our model, we did some calculation and plausibility checks. We can check for some mobile flood protections that may not be in the digital elevation models, but will be installed in case of a flood. For example, you can see here, this is a picture from, I think, Cologne. The water level is really high. It's nearly on top of that mobile wall. And if a flood warning is coming, the city will implement or install all these wall parts to prevent the city from getting flooded. So this is a short film. You can see the water is running and filling its riverbed, and then finally you can see the first weak points of it, and the water is getting out of its bed, flooding the grassland areas, then flooding where it comes together. And then some rain starts to even flood the urban areas. You can see how it's going through the streets, filling the soccer stadium. And this was our school. So it was built a little bit high up, so it was not affected by the flood, but the place where they wanted to build their new building is flooded, as you can see. And when we now calculated these, we were able to calibrate it on the flood hazard maps. This looks like this. So you can see again, what we just saw in different blue colors, the water depth here, and where the water will stand and what areas are endangered. And in all of these areas that are endangered in a 100-year flood, there is in Germany a construction ban in these 100-year flood areas. But this would mean you can never build a new building inside of these areas, and that's a bit harsh. So there's an exception approval possible if you can prove that there are no negative impacts on your neighbors and if there are no negative impacts on the water levels, so that all the infrastructure will not get harmed with your new building. And we can prove that through a hydraulic modeling. And the overall aim is always to protect the human life and to prevent the potential damage. So what we did here was to build up the model one time for the actual state, then add the new building. This blue box. We wanted to build it this large in the first try in the blend state number 1. Then we calculated it, displayed us the water levels. And as you can already see, on the left side there's the actual state, and the water level is displayed in a much lighter blue, which means a lower water level than on the right side. And when we build the difference, it shows us that this whole urban area and all the neighbors upstream of our school will result in water levels with at least up to 2.5 centimeters more water. So it's not allowed, and well, it's not allowed to build your new building just like this. So we sat down with the architects and discussed what can be done, and it finally resulted in building the new school building like this, where we have ramps to enter the building, and we have the underground, or in the basement, we have such little holes, and the whole area beneath the new building was intentionally for parking your cars, but in a flood event, it's an area for storing the water volume. So water will run through all these holes and these ramps and just fill this area beneath the building. Then we once again calculated our new plan state 2, compare it to the actual state. And what we can see now is that they actually have kind of the same water level now for the neighbors. If we do the difference, we can see everything is green. Green is, plus minus 2 change in water level. The only negative part is really right in front of our building, but no one lives here, and so it's okay. And we have here a water level that's even 5 centimeters lower than in the actual state. So you can build your building like this. You have your proof that it's no negative impact for your neighbors and no negative impact for other infrastructure or whatever. So you are allowed to build this building like this, and you know how high the water will stand in the 100-year flood. So you can put it just as high as necessary to prevent damage on your own building. So this is how we deal with river floods. And then we have heavy rain events as a second reason for floods happening. Heavy rain events are defined, or the definition is that they are events of short duration and high intensity, and it's very difficult to predict them. And because of that, very difficult to predict, there are, of course, very short warning times. And this is a graph I brought from the German weather service. And they say a heavy rain event starts at 15 millimeters in 1 hour. And it goes up to more than 60 millimeters in 6 hours. So just for you to compare, the annual average rain in Germany is around 800. So the 60 is a bit less than 1/10 of what happens in Germany in a whole year. And this is how floods will occur. Not only the heavy rains, but we start on the left side, and this firstly explains the causing of river flooding. So we have large continuous rain for really a long period, for example, and the soil is already saturated, and we have it's just too much water for just seeping away. So we have a surface and subsurface runoff, and it all runs off to the river, and the river level is growing and growing, and then you have your flood due to river flooding. And on the right side, it explains the causing of heavy rain events. This, as I already said, are just with short duration, high intensity, and it's hard to say this will happen here and then. And it gets even worse when the human keeps building its cities and streets and so on, because in a natural water cycle, on the right side, we have a heavy rain event, so a lot of precipitation here coming down. Then we have, because we have plants, we have grass, we have some bushes, some trees, for example. We have also some really huge amount of evaporation and transpiration. We have the interception on the plants as well. And we just have a smaller amount of runoff here. And of course, the water is, because the surfaces are not sealed, the water can infiltrate in the soil and results in a groundwater recharge, but this needs some time, of course. And then on the left side, we have the anthropogenic modified urban water cycle with sealed surfaces due to streets or roofs or whatever, because, well, the water can't infiltrate. We just have very few rates of groundwater recharge. The water can't seep away, and we have no vegetation, so we have no interception. We have just a little bit of evaporation, and the most part of the water that's coming down is not held back by plants, but it's running through the streets. So we have a heavy surface runoff on these streets. And when these heavy surface runoff on streets happens, this is how the streets could look like, or what happens actually in your town and in your house. You have a water level that is higher than the sewage system and coming out of the system. And if the water level is even higher, then your not your devices, but for example, your toilets here, the water level is higher than your water level inside of your building. The pressure, of course, it just pressures water into your basement. Then we have a lot of water running through the city, running through the streets, and massive destruction. For example, I brought this picture. This was 2 years ago, I guess, in Valencia. So we had a heavy rain event in a canyon-like countryside, and the water just ran through the city and took everything with it.
5 more minutes, Philip, to allow for engagement with your participants. Thank you.
Excuse me? I didn't understand what you were saying.
I'm saying the presentation, if you could wrap up the presentation in 5 minutes to allow 10 minutes of discussion so that people can engage and ask questions. Thank you.
Okay, yeah, that's possible. So how do we prevent people to end up like this? So this compared to our flood due to river floods, we also have these heavy rain hazard maps. And these show us how the water flow path will run through the city, and you can see if you are endangered or not. And to calculate these heavy rain hazard maps, we use again our hydraulic models. But as input, we don't have a river. As input, we have a rain, and the rain is coming down everywhere. So we just take the rain that really is effective. So we use not the overall precipitation, but the effective precipitation. And this is the part of the precipitation that is not retained or seeps away, but the one that runs off directly. As you can see on the red curve, we have a street. There's no holding back from grass or plants, and everything is sealed. So we have a really high effective precipitation. And on the blue point, we have grassland, and we have natural soil that water can infiltrate, and we have a much more lower effective precipitation. And this is the input for our model in a heavy rain event. And I brought this example. This is well, a village where heavy rain events happened really often because the topography really makes it easy for water to just accumulate and run through the city. It comes here, these natural slopes, then accumulates in the middle and runs through our city center. It even gets worse when you look at these ways, because on the left and right side there are kind of small dikes, so the water stays on these streets. The streets, well, it resulted in much energy and the water level, and the water is running really fast to the city center, and then it ends up in these sewage pipe, and of course it's too small to properly drain the incoming water, so it will just rise and rise and at some point just flow over it. So we have the last video for today where we calculated this. Here you can see the small entrance to the sewage pipe. The water is coming up from the topography, getting here, then the water level is rising, it's overflowing, and then at some point it's just really gets kind of pressured through the streets. So sometimes there are also requirements for new construction, even if you're not in a river flood 100-year area. But if you want to build your building safe for heavy rains, and so you can also check if you have no negative impacts for your neighbors, if you have no negative impacts on the water depth that will happen due to your new building. You can calculate the velocity, and of course you want to protect your new building that you're building here. So then this is the end of my presentation. Thank you very much. And I'm looking forward for your questions.
Thank you so much, Philip, for such an insightful presentation. Colleagues, if we could give Philip a round of applause. I'm sure that we can do even using the online hands for that purpose. Thank you. We'll leave the next 10 minutes for questions, comments, reactions to the presentation. Colleagues, please feel free to engage. Yes, I think it's Joanna. Mr. Thinde, please go ahead with your question or comment.
Good afternoon, good evening, everyone. Thank you, Philip, for your presentation. I was just curious because you mentioned that flood can be caused, you can also have flood due to groundwater. I just wanted to inquire, what are the different factors that go into having issue of groundwater flooding? Are we looking at the hydraulics? Are we looking at the water table? What are the other factors that we consider and say that we are experiencing groundwater flooding? Thank you.
Well, the groundwater flood is you can imagine if you have a dike near a river, for example, and the river is growing up, the water level is rising, but your dike is still high enough. So there's no flowing over your dike or your dam, and the area behind these would be safe. But because the water level is so high, the water pressure, even in the underground, is high, and it just the pressure kind of puts the water beneath the dike and the dam and pushes the water out of the ground behind your dam. And so you're also affected by a flood, even though your dike is high enough and it's not overflowing it. Was
Thank
that
you.
your question?
Yes, thank you very much for the clarity.
Thank you so much, Joanna, for the question and Philip for the response. Any other reactions, colleagues, including team members of the WaMiSAR consortium? If you would want to come in and say something to add on to what Philip has shared with us today. Okay, I see Teba is there. Teba, please come through. Colleagues, Teba is one of our coordinators, and she has been ensuring that the WaMiSAR project continues to run smoothly behind the scenes. Teba, thank you so much for joining us, and the floor is yours.
Thanks, Reni. Thank you, Philip, for the nice talk. It was very clear. I have a very naive question. At the beginning, you showed the time series from the gauge with a predictive model, the yellow and red lines. Is this an independent model from the one then that you presented on the 2D spatial map, or are they somehow related? Can you predict from your hydraulic model how the water height will be in the future, or is this totally unrelated?
Actually, it's not the same model. It's it's a really complex model, and it's run by the LUBW. So yeah, we don't really calculate it here at our office. We build parts of this model, and it's often 1D models because they run so quickly. And then we give it to the LUBW, and it's run there and fed there by the input data, and they publicate their forecast.
Nice. I thought the model, the predictive model, was based on time series. Could it be?
On what time series do you mean?
The one from the gauge with the different heights?
The one I have shown?
Mm-hmm.
I share the screen again.
Yeah, this
Can
one.
you see it?
Mm-hmm.
I mean, this one. And what's your question?
If this is based on time series only.
Well, it's based on the different weather forecasts, and they are the input for the hydrological model. And then we have different hydrological models running with different outcomes, and these are in the range of shown here.
Mm-hmm. Okay. Thanks.
Thank you so much, Philip, and thank you, Dr. Tebe. Colleagues, if there are no additional hands, I'll leave this out. Okay, Joanna, please come through. And I see Junius. So soon after Junius, I think let's allow Junius first, then Joanna. And let's use the next 2-3 minutes before we round off. Thank you.
Okay, thank you very much, Prof, for the wonderful presentation. So I would like to know the tools that you are using for modeling. Is it Heke, GMS, something like that, or which tools are you using?
Well, for the one-dimensional modeling, we have a in-house solution, that it's also the core of what's running at the LOBW or the official forecast station. And for two-dimensional modeling, we're using Hydro AS, which is a software made by Hydrotech, and it's a company in Aachen, Germany. But we also use HECRAS sometimes. So.
All right, thank you very much.
Joanna, please come through.
Thank you, Rennie. Actually, I just wanted to find out if these models have been tested in the African context, and how reliable are they? Because in most cases, we find that some models are quite very good when we are predicting extreme weather conditions, particularly in the Western world. But when we come to the African content, we almost face some issues in terms of what the kind of data we have available in our African countries. So I just wanted to know, has it been ran for the African context? Thank you.
Actually, I don't know if it's when on the African continent, for example, for our heavy rain model, which is based on the Hydro AS two-dimensional model. But I don't see the problem why it should not run here, because well, the difference is maybe the amount of water that's infiltrating. And if you erase this fault, even when you calculate from your precipitation to your effective precipitation, and then you just have the effective precipitation as an input in your model, it should work, as I think so.
Thank you so much. In the last 2 minutes, Professor Stefanora, would you want to say something to close our webinar for today? And probably appeal to our African scholars that are also present online, if they're interested in making a presentation on this platform, to get in touch with either myself, Professor Stefanora's email that is on the platform, as well as Teba. We'll be happy to integrate you into the webinar series. Thank you. Over to you, Prof. Stefanora.
Yeah, thank you very much again, Rennie, and also special thanks to Philipp. I think we all have seen a very interesting and thoughtful presentation on the use of models for forecasting stormwaters, floods, and many more issues also you are facing probably in Africa. I think it was very meaningful, the presentation, and we got a lot of information by this presentation. My final question would be, Philipp, could you also link these models you have used for the minor residue deposits? So what would happen if we have a real extreme storm water rain event falling on or affecting a minor residue deposit? That could mean there's a lot of erosion, and the particles from the deposits would spread over perhaps larger areas, even into the settlements which are adjacent to some of the deposits. Could you use your models for that as well?
Well, we could use the base of it when we calculate heavy floods or heavy rain floods in Germany. We don't really integrate the erosion topic, but when it comes to the deposits, it's really important. And you can add a feature or a model to this Hydro AS, where you can also which includes things like erosion and the force that's happening on the ground, on the riverbed, for example. So I think you maybe could calculate the erosion that's happening due to different intense heavy rain events.
Mm-hmm. Okay, I think this is going to be also something we can consider in our special project, WaMiSAR, if such extreme rainfalls would hit such a residue deposit of mining material. Okay, so thanks again, Philipp, for your excellent presentation. Thanks to all of you who participated here in the webinar. The next webinar will be announced soon, and therefore I have the honor also to close these days presentation and coming together. And I wish all of you a very good time and hope to see you soon for the next webinar in good shape and good health. All the best to you. And again, thanks to Teba, Philipp, and Renny. Goodbye.
Thank you, Prof. Thank you, colleagues, for making the time. For those that are still part of the conversation, there is a link that was shared by one of our postgraduate students. If your time avails, please try and respond to the survey at your convenience. Thank you and goodbye.